think you might be able to see if we can turn these lights down just a little bit up front? Okay. It's a pleasure to be here, and everybody thinks I'm from Blacksburg, Virginia, but I'm actually from Blackstone, Virginia, and Blackstone is 50 miles southwest of Richmond, Virginia. So we're in the southern Piedmont of Virginia. We're at about 420 feet of level, and our temperatures there are pretty extreme during the summer months. Not uncommon to go walk outside in the summer, and when you take 2 steps, you just totally sweat because the humidity's high and the temperature's in the mid to high 90s. And it's quite a bit different environment than Blacksburg, where our main university is. We're about 180 miles directly east of our main university. Our climatic conditions are much closer to North Carolina State University than our home university, Virginia Tech. So today I want to talk a little bit more about drought and how we can start to manage our pastures for increased drought tolerance. In the title of my talk is Adapting to a Changing Climate, Managing Pastures for Increased Drought Tolerance. And I just want to start out just with a couple slides on the climate. And I think these are all taking a look at. This is from NOAA, the National Climatic Data Center. And this shows CO2 levels in the atmosphere over the last about 450,000 years. And what's interesting, when you go back and you look at those, it's a cyclic pattern. They go up and they go down. They go up and they go down. What's interesting about this graph, it isn't until recent times, about 1950s, that we really start to see these things exceed 300 parts per million CO2 in the atmosphere. And this is probably closely correlated with the increased use of fossil fuels. So we're burning a lot more fossil fuels and we're releasing a lot more carbon dioxide into the environment. This is temperature.
The most important thing that
the current time, and we've seen a steadily increasing trend in temperatures. And I know you're looking at this and saying, wow, 1.2 degrees Celsius. This is on a global basis, though. So a change of 1.2 degrees, that would be, was that about a little over.
I didn't even spend that money. And I think that's what this program was mainly about.
On the whole global. So that's a pretty major temperature shift in the last 100 years.
And
I was getting ready, I came across this paper, and it's from the Massachusetts Institute of Technology from their climatic center there. And what this map is showing is the mean difference in the number of drought months. So what they did is they went back to the last century and they looked at how many drought months we had for different regions of the state. And then they made a prediction of what's going to happen in the first 30 years of this century. And where it's red, if the number was 0, that means that we would have the same number of drought as we did the last century. And that would be right here, this kind of greenish yellow color in the center. If it's red, then it means we're going to have more drought months. And if it's green and goes towards the green side, that means that we could have less drought months. This is a prediction. But I thought what was interesting was they're not predicting an even spread of drought across the country. What they're predicting is that we're going to have a greater incidence of drought in certain parts of the country. And that's certainly what we're seeing right now in the southwestern United States. Luckily, as we move up into the upper Midwest and the northeastern United States, we could actually see less drought as we move into the first 30 years of this century. How much faith do you put in this? I mean, we can't get the weather right 3 days out, let alone 30 years out. But I thought it was interesting. And we'll see how true this actually comes out to be. I'm going to talk about pasture management today and managing pastures for increased drought tolerance. And in order to really do that, we have to talk a little bit about forage plant growth. And I think this is a very, very important topic, and one that we often don't talk enough about. And there's reasons we don't talk about it. One, it's not easy for people to understand, and it's not easy for me to talk about. And And so a lot of times we'll just kind of gloss over this. But it's really a critical principle to understand how forage plants grow. And if we understand how they grow, we can really manage the forage plants much better in a rotational crop. We're going to spend just a couple topics I want to cover underneath
Town boy, he grew up on a farm.
This is the physiology, and that's just a fancy word for what's going on in the plant and the vital processes that are taking place. I'll talk a little bit about the morphology. That's that fancy word for the physical structure of the plant. How's it grow? Does it grow up? Does it grow
Taking all my elective business.
Does it have stolons and rhizomes? What kind of root system does it have? The physical structure of that plant is what morphology means.
So this time,
Then how these two things, the physiology and the morphology,
income taxes.
interact to determine how we should be managing that plant under grazing.
What?
Thank you.
Graham,
I always like to start out and talk a little bit about what we commonly consider the smallest part of the plant, and that's the plant.
income tax.
But in reality, even within the plant cell, we have what we call organelles. And organelles are very specific structures within that plant that have specific functions. And we're not going to talk about all the organelles in the plant today because we don't have time. But what we are going to talk about is a few key structures.
Scrap.
The key structure I want to talk about is the vacuole. And the vacuole in the cell is a large structure, and this can take up about 80% of the cell volume. It has a couple important roles, and the most important role is that it maintains turgor pressure in that plant. And you're saying, what's turgor pressure? Turgor pressure is what keeps the plant rigid and upright. When we get into a drought and that plant starts to wilt, we lose turgor.
My cows.
The way the vacuole does that, if we think of this as our cell, and the cell walls are not quite actually like this rigid plastic. They're kind of like a canvas bag almost, so they're kind of a semi-rigid structure. If we think about this in a cell, the way the vacuole keeps it inflated it actually blows up inside that plant cell and pushes out against those cell walls. And when it does that, that plant remains upright and rigid. It has turgor pressure, is what we say. When this plant undergoes a drought stress, what happens is this vacuole doesn't blow up with air like this balloon, but rather with water. And when we undergo a drought stress, what happens is we don't have enough water to keep this vacuole inflated. And as we lose the turgor pressure, the plant wilts. And we're going to talk about how a plant responds to drought a lot more as we get into this talk. The other structures I just want to mention is the chloroplast. And the chloroplast is important because it contains the machinery to carry out photosynthesis within that cell. And we'll talk a little more about photosynthesis. And then the mitochondria, also called the powerhouse of the cell. And what that does is it releases chemical energy in the form of sugars and carbohydrates. It releases that energy so that in a controlled manner that can be used for growth and maintenance of that plant. So let's talk about photosynthesis. Photosynthesis is, I know you guys think you're going back in high school biology class, but that's okay. A little bit. We're not going to stay there too long. But photosynthesis is by far the most important biochemical process on Earth. And in this process, we take light energy from the sun and we convert it into chemical energy in the plant. And we do that with the following equation. And so we take carbon dioxide from the air, we take water from the soil, and we turn them into sugar and a very important byproduct for us, oxygen. And this all takes place in the chloroplast of the cell. That's that structure that had the machinery for photosynthesis. And the whole process is driven by light energy from the sun. Now, when we talk about photosynthesis, there's two major photosynthetic pathways that we find in our forages. We have the C3 pathway, which we find in our cool season grasses. The C3 comes from the first acid formed in the photosynthetic process, has 3 carbons. That's where we come up with 3CN. We find the C3 pathway in our cool season grasses. This pathway is very well adapted to carrying out photosynthesis at cooler temperatures. We're going to get optimum or maximum photosynthetic rate when the leaf temperature is around 70 degrees Fahrenheit. So that means we're going to get the most growth from a C3 grass in the spring and in the fall. but not much going on in the summertime. C3 grasses would include things like tall fescue and orchard grass and Kentucky bluegrass. And what happens in the summertime is we get a decreased rate of photosynthesis and growth during the summer months. We call it the summer slump. What's important to remember is that this rate of decreased growth is because photosynthesis is temperature limited during the summer months. Now, in contrast, C4 or warm season grasses are more efficient at carrying out photosynthesis at higher temperatures. They don't reach peak photosynthesis until around 90 degrees Fahrenheit. And they're much more efficient at using water. They'll produce about twice as much dry matter per year compared with our cool season grasses. And that's because their growth is not temperature limited during the summer months. All of our growth in our warm season grasses are tucked right into the middle of the summer. Sometimes, when I throw that chemical formula up for photosynthesis, people's eyes glaze over and they just turn themselves off. So I like to use a little cartoon model for photosynthesis too. And it gets some important points across in terms of pasture management. If we think about the plant leaf as our photosynthetic factory, we're producing a product. And that product that we're producing is sugars and carbohydrates. And like any plant, when we produce a product, we need raw materials. And our raw materials for photosynthesis are sunlight, water, nutrients, and carbon dioxide. They move into our photosynthetic factory, produce a product which is sugars and carbohydrates. And a very important byproduct for us is oxygen being released into the atmosphere from our photosynthetic plant. And then that product can go two places. It can either go to the warehouse where it's stored up for later use, or it can go to the consumer outlet. And the question always is how does a plant determine where it goes to? Does it divide at 50-50 or 60-40 or 70-30? And the answer is that in the plant, what always gets first billing is growth and maintenance of this plant, or what we call the consumer outlet. So first, the growth and the maintenance energy needs of that plant has to be met. Only when we have excess sugars and carbohydrates being produced do the extras get shifted into this warehouse. And this warehouse is very, very important in the plant because it's storing up energy that can be used during periods of stress, can be used for regrowth after defoliation, can be used for regrowth in the spring after going through a winter dormancy. So keeping that warehouse as full as we possibly can is very important in terms of pasture management, in building a robustness into our pastures. Talk a little bit about plant morphology. Just remember that's a fancy word for that physical form of the plant or the structure of that plant. When we look at our grasses, we have two kinds of grasses, and Ozzy kind of covered this yesterday in her lecture. We have what we call our bunch-type grasses. They include things like orchard grass and tall fescue that kind of grow in clumps. Now, when those clumps are really tight in the field, it looks like a nice sod, but really those plants are a bunch-type plant. And then we have our sod formers, things like Bermuda grass and Kentucky bluegrass, which have structures called stolons and rhizomes. And those allow that plant to spread out over the soil surface. And they form a dense mat, and that's what we call our sod formers. Just by knowing a little bit about the morphology of a plant, we can look at a plant and we don't even have to identify it, and we can tell, well, because that plant grows upright like this, it's probably going to be a little bit less tolerant to close and frequent grazing than a plant that grows prostrate close to the soil surface, where a lot of that plant is safely below the grazing height of the animal, which is going to be much more tolerant to close and frequent grazing. So just by knowing
We'll go attendance at our workshop, and then to finish out,
tell how we plant under grazing.
get a
couple other things to point out is the root system of the plants. Our grass plants tend to have a fibrous root system. Our full season grasses are going to be in that upper 10 inches of soil, about root system. And they're going to have a very dense net of fibrous roots. That makes that plant very efficient at capturing nutrients that are applied close to the soil surface. In contrast to that, our legume plants tend to have a taproot system. And that penetrates the soil much deeper, 4, 6 feet or more, depending on the legume we're talking about. It has one dominant root that goes down with some branches off of it. That makes that plant very efficient at finding moisture in times of dry conditions because it can reach deeper down into that soil to pick moisture up. And that's one of the things that makes alfalfa so much more drought tolerant than a grass. The other structures I wanted to point out today was these modified stems, and they're called rhizomes and stolons. And we find these structures in our sod formers. And a rhizome is simply a modified stem that grows just below the soil surface. And a stolon is a modified stem that grows just above the soil surface. And they're important because they store carbohydrates. And if you ever see this abbreviation in my talk, CHO stands for carbohydrates. And carbohydrates are an energy source in that plant. And they store energy in these stolons and rhizomes. And the neat thing about that is that they're close to the soil surface or just below the soil surface. So they're safely below the grazing height of the animal. Okay, so we have a defoliation event taking place. And I want to tell you a little bit about this picture. It's not a cow, of course. It's a horse, and they're tight grazers. And this was from a horse farm in southeastern Virginia. And this was a tall fescue pasture. Is that tall fescue that's there now? No. And horses are notorious for spot grazing. So these horses in this pasture came back to the same spot in this tall fescue pasture and grazed it over and over and over and over again. And eventually the tall fescue died. And so what came in was a natural grass, and this is Bermuda grass, just an ecotype of Bermuda grass. And Bermuda grass is very tolerant to close and frequent grazing, as you can see in this photo. It actually will thrive with a little tighter grazing management. So the question that I have for you is we have a grazing event here. If we have enough water and we've got a good soil nutrient status, what do we need for this plant to regrow after it's been defoliated? Leaf. What's the leaf doing? Yeah. So it's photosynthesizing, and he's right on track. What we need is energy for that plant to regrow with, and that leaf is going to capture that energy. And energy comes from two places. Leaf area remaining after grazing, so that photosynthetic factory that we talked about earlier. The closer we graze a pasture, what happens to that photosynthetic factory? The smaller it gets. And the smaller it gets, the longer that pasture is going to take to regrow. And this is, of course, species dependent. Some species are more tolerant to close and frequent grazing than others because of the physical structure of the plant. The other place that energy comes from for regrowth of this pasture is from stored carbohydrates in that plant. So keeping that warehouse full is very important because it's going to provide energy for regrowth and persistence of that pasture after grazing events and after stress events. Nonstructural carbohydrates are stored substances that provide energy for regrowth and persistence. So that sugars and carbohydrates in the plant are going to provide that energy for regrowth and persistence. And there's lots of factors that affect the carbohydrate status of the plant. But basically anything that impacts photosynthesis is going to impact the carbohydrate status of the plant. And again, this little diagram just shows the same thing we've been talking about. We have photosynthesis going on here. We have sucrose being produced, which is a sugar. And that sugar can go to two places, either to storage for later use or to growth and maintenance of this plant. Growth and maintenance always get first billing. Only after we're meeting the growth and maintenance requirement of this plant does the extras get shifted into storage. And if you understand this concept, you really understand the whole basis of rotational stocking. We're giving pastures time to rest after a grazing and rebuild their photosynthetic factory, and then store up some sugars and carbohydrates, store up that energy for later use by resting that pasture between grazing events. Okay, this is a table. It's a little busy, but I'll point a couple things out. This shows the location of carbohydrate reserves within the plants. And is it important where the plant stores its carbohydrates at? Does it matter, you think? I would say yes since I'm showing you a table, right? But take, for example, orchard grass. Orchard grass is a bunch type that's going to store its carbohydrates in the stem base of the plant. Okay, so we're in an orchard grass pasture and we graze it really close down. What are we doing to that orchard grass plant? Killing it. We're putting the double whammy on it, right? Remember, it's got its energy for regrowth from leaf area left after grazing, that photosynthetic factory, and then from stored carbohydrates. So if we graze it close, what do we do to the leaf area? Increase it significantly. What else are we doing when we graze it close? Taking our warehouse out. That's exactly right. Doing it once isn't going to kill a pasture, but certainly if you do it multiple times in a row, it's going to kill that pasture. I think one of the worst things that have happened to orchard grass hay stands is the invention of the disc mower, because we can cut those fields so closely, and that's one thing that orchard grass doesn't really like, is that close.
Payoff for meadows with that's exceptional. Quite as good as other meadows.
So let's look at another plant,
Produce
Bermuda grass. Now, Bermuda grass,
quality sometimes.
orchard grass stores its carbohydrates in stolons and rhizomes.
roll.
Remember that
Go back.
modified stems that go
Some of that
the surface or right below the soil surface. So even when we graze that close,
with help and minerals to distribute the minerals and or
plus Bermuda grass has a lot of
to help.
very close to the soil surface.
I enjoyed taking samples with
One of the points I wanted to make
it's kind of
it's not that we can't use plants like orchard grass in grazing systems. We certainly can, and certainly should in many cases. The point I want to make is that we have to manage those plants a little bit differently. And so when an orchard grass situation or other cool season grasses that are storing their carbohydrates in the stem base, we want to leave that stem base and we want to leave some leaf area on that pasture.
season cattle than we do this winter, and it's a little colder this winter. We got to the 1st of January this winter, but we had a few more cattle, and the temperature's been a little colder. And, we've seen a huge benefit from rotational grazing. There's challenges to that.
And ahead of its times when it comes to forage maintenance.
Just
These diagrams in these old publications are still very applicable to today.
you got water and trough.
Alfalfa is an example of carbohydrate
I'm sure Hendershot will touch on it.
plants. Alfalfa is
How they're
100% dependent
plant
on
animals.
carbohydrates for regrowth.
Is in
When we cut an alfalfa field, what's it look like? Do we leave
Off.
a lot of leaf area when we cut an alfalfa field? No, it's mostly what? Just a little bit of stubble is left. So that energy
during this program.
regrows pretty vigorously. It comes from somewhere.
It's a good idea to keep
It comes from stored carbohydrates.
on that too.
And when we defoliate an alfalfa, it starts to regrow. We get a dramatic decrease in the stored carbohydrates in the taproot of the plant. And as we get up to 6 to 8 inches tall and we start to rebuild that photosynthetic factory, look what happens. The carbohydrates start to build back up. And by the time we reach the next cutting,
Like I said, the biggest thing that I got from this was just we look
cut levels of carbohydrates. And the plant has fully grown and we're ready to harvest. All forage plants have a carbohydrate cycle. It's most pronounced in alfalfa, but all forage plants will have likely use of carbohydrates after defoliation events. What would happen in the case of alfalfa if we let it get 6 inches tall and then we came in and we grazed it off or cut it again? We get another decline in carbohydrate concentration in the roots. And if we do that over and over again, we're eventually going to all the carbohydrates reserves out of that plant. And that's what happens in a continuously stocked situation. When we have a high grazing pressure and continuous stocking, every time that plant tries to regrow and rebuild that rebuild that photosynthetic factory, and we remove it, we're drawing the carbohydrate levels down. So what happens over time, we won't kill a pasture doing it once or twice, but we're going to draw that carbohydrates down, and it's going to come back slower and slower and slower, and then that stand's going to open up, and what comes up when we open the stand of grass up? What comes up in a bare spot? Weeds, that's right. All right. So I've got a plant. This is a diagram from Dr. Blazer's publication. This is a grass tiller. And what it says here is once this collar is present, then we don't get any, this leaf is not going to regrow. This collar is a little structure right here. And the question I have for you today is, what do we do with that leaf? We know that most of the nutrients in a grass plant are in the leaves. So what do we do with that leaf? Do we leave it or do we graze it off? And don't answer yet. I brought a few Virginia grass tillers with me today that I want to show you all. So that's the collar structure right there. That's the collar right there. Yeah, I just pulled these up from our yard at the research station. Right there is a collar structure. Now, I'm sure Gary's seen a collar structure before, but right here's this is called the collar. So this leaf is not going to regrow once that collar shows. I'm going to take a few back here and let you all look at that. That's the collar structure right there. Didn't bring quite enough, you see? That's the collar. So this leaf right here is not going to grow anymore. Oh, well, you don't need to see a collar structure. Raise up. This is the collar, so this leaf isn't going to regrow anymore. That's the collar structure there. So the question is what do we do with that? What do we do with that leaf? Well, first tell me what color is that leaf where the collar structure is showing? Is it brown and dead? It's not a trick question, I promise you. What color is it?
It's green.
Green. Okay. What's green mean?
Grow alive.
Okay, so if it's not growing anymore, but it's still green, what's that mean?
Photosynthesizing.
Okay, so where do you think that energy is going in that leaf? That's collecting from the sun through photosynthesis.
Storage.
Back down into that plant to help propel the growth of that new leaf coming out. So the answer to the question is, should we graze it off? No. It's helping to fuel growth of that new leaf that's emerging from that plant. So the answer is that we should stop. And this is one of the bases of rotational stopping. We need to retain residual leaf area in the pastures. That's going to fuel new growth in that plant. This is a little bit busy of a diagram, but I think it's very important that we talk about it. And if you look at one diagram when you go home again, take a look at this one because this is very important to understand. So it talks about the carbohydrate and leaf area interactions. So I divided this diagram. If you look at the plants on your right, so that's this half of the diagram here, these plants have a high carbohydrate status. That would be similar to being rotationally stocked. So they would be grazed and then rested, grazed and then rested. So we have that warehouse in that plant full of carbohydrates. Now, the other side on your right would be a low carbohydrate status. So that would be something that was continuously grazed off. So every time that plant started to regrow, the cow would come in and nip it off over and over and over again. So it has a low carbohydrate status. And then they did one other thing. They either left 2 inches of leaf, like we just talked about doing, or they grazed it all the way off. And then they looked at what regrew. And when we look at a plant that had a high carbohydrate status and 2 inches of leaf area, we had 1 inch of regrowth and we had 4 new tillers formed on that plant. If we go to the opposite side where we had no leaf area left and a low carbohydrate status to start with, like we might find in a continuously stocked pasture, we had half as much regrowth and fewer than half as many tillers formed. I know that's a lot to digest from that diagram, but this really shows us how important it is to leave some residual leaf area and to rest our pastures between grazing events. We're going to increase productivity of those pastures, and we're also going to stimulate tillering in those pastures and have dense, healthy stands of forage. Over time, what would happen in this pasture? We're going to thin it out, and weeds are going to come into this pasture, and the productivity of this pasture is going to drop greatly. This is a real-life accidental demonstration, and this was in southeastern Virginia, the Tidewater Research Station. They had a tall fescue trial there, and the guys at the ranch were helping me maintain the trial. So what they did was they thinned around my crops really good. Less than 2-inch cutting height, mowed it every week, and that's what it looked like. We just finished harvesting these crops to a 3 to 4-inch cutting height, and look at how much more leaf area is left. Which one of those do you think is going to do the best if we get into a drought stress? The 3 to 4 inch that has been cut and then rested for 30 days. So the point is this close and frequent grazing in pastures can really put some rest on pastures, especially during the summer months. And what we do to the top of the plant also impacts what's below the ground. This is an old study, and just because it's an old study doesn't mean it's a bad study. This was from the 1950s by Kreider, and he did a study called a root growth stoppage study. And what he looked at was removing different levels of the shoots of the plant. So in this first treatment, he removed half of what was above the soil. So 50% removal of the shoots stopped root growth. A single removal of 90% of the above ground material stopped root growth for 17 days. When he clipped those pots 3 times a week, root growth never resumed. That's what happens in a continuously stocked pasture, especially if it's at a little bit higher of a stocking rate than it should be. Every time those plants start to grow, those animals clip that growth off, and that root system gets smaller and smaller and smaller over time. And what he found was when you remove 40% above ground shoots, root growth never stops. And that's kind of where we get this rule of take half and leave half in pastures. And that really promotes a healthy root system within the pasture. So the point I want you to take home is that what we do to the top of that plant translates to the bottom of that plant. We never talk about that hardly ever, but what we do to the top of the plant has significant impact on what's below the ground. And what's below the ground is going to have significant impact on how that pasture fares during moisture stress. All right, this is just a nice diagram to kind of put things together that we just talked about. So we've got some different plants on. If we look at, for example, this orchard grass plant, we've got a pretty tight grazing height here, a little bit less than 2 inches. When we defoliate that plant to a little bit less than 2 inches, how many leaves do we have left on it? A lot? Not much. Where did orchard grass store its carbohydrates at? In the lower stem. So not only did we remove all that photosynthetic factor, we also removed that storage organ for that plant. What's it going to do under that close and frequent grazing? Well, not so well. Not so well. So we're putting the double whammy on this plant, removing its photosynthetic factory and its storage organ. Take something like Bermuda grass. Remember we store the carbohydrates in the stolon and rhizome system safely below the grazing height, plus we've got a lot of leaf area close to the full surface. That plant will fare much better in a close and frequent grazing situation than the orchard grass will. And we know all this because we understand a little bit about how forage plants grow and a little bit about how they interact with the morphology of the plant, the physical structure. Rotational stocking is a powerful tool, and I just want to show you this slide real quick on botanical composition. Botanical composition means what plants are present in that stand of pasture. And here we have a mixture of alfalfa and orchard grass. And just by how we manage this mixture, we can shift that botanical composition towards one plant species or another. And in this example, we have a close grazing height. The alfalfa dominates underneath that close grazing height. Why do you think that is? Anybody know? Why does the alfalfa dominate under that close grazing height? Where does it get its energy at for regrowth? From the taproot. So when we graze it tight, we're not hurting its regrowth as much because it's more dependent upon carbohydrates from the taproot for regrowth. In contrast, orchard grass is dependent on a combination of stored carbohydrates and leaf area. So when we graze it tight, we're removing that leaf area or that photosynthetic factory, and that tends to reduce the vigor of that orchard. In contrast, if we raise that grazing height, we tend to favor the grass in that mixture. This is a powerful tool. We can manage botanical composition in our pastures if we understand a little bit about how mixtures of forage plants respond to grazing. If we want to shift a pasture away from, say, white clover growth towards the grass growth, what do you think we should do? Let the grass grow up. So don't graze it quite as tight. And we can use it to manage grasses within grasses. If we have mixtures of Bermuda grass and fescue, we can favor either one of those in that stand by how we manage that grazing on that stand. All right, so let's talk a little bit about drought. This is a study from the 1970s that looked at long-term weather records for the Northeastern United States. And basically what they concluded was that we're going to have a moderate drought 1 out of every 5 years and a severe drought 1 out of every 10 years. Does that sound about right? I think it's pretty close. I mean, they don't always come exactly on that schedule, but that's probably pretty close. And the interesting thing is that it's always a surprise. It's like, man, I've never seen one of these before. In reality, we see one about every 5 years or so, and it shouldn't be a surprise. And we need to think about managing our pastures, not just when we get into drought stress, but really managing pastures to be ready for that drought stress every day. And that's kind of what the rest of this talk is. And I'll put in a plug for the farm management plan. D-Day calving season to be real formal plans, but I think everybody that has livestock and forages should sit down and really think about, what am I going to do if I get into a bad way with a drought? You know, what's my plan? What steps am I going to take? How am I going to manage my pastures? How am I going to manage my livestock? And just write it down on a paper. And then when it happens, you're ready for it, and you're not having a knee-jerk reaction. You've already planned for it, and it's going to take a lot of stress off of you and your family. Okay, let's talk a little bit about water relations and plant growth. Everybody knows water is the overarching factor for pasture productivity. And not so much the total amount of rainfall we get in the season, but how that rainfall is distributed across the growing season for that particular forage species. A lot of times we can get a lot of rainfall for the total year, but if it doesn't come during the right time in the summer, then we're in a pretty serious moisture deficit. And we always talk about annual averages, and my economist at Virginia Tech says an average is like sticking 1 foot in a bucket of ice cold water and the other foot in a bucket of scalding hot water. On average, you're pretty comfortable, but it hurts like hell. So when we get into a drought stress, what's the plant's ultimate objective? Is it to grow and produce forage to feed your animal with during that drought stress? Yeah. I've got bad news. It's concerned about your livestock because it's not really. Ultimately, all it wants is just survive that drought stress. And eventually it's going to do that by maintaining its growing point. Now, when a plant undergoes drought stress, things happen in that plant. We often think of a plant going from well-watered to drought stress as like we're flipping a switch on or off. And that's not what happens in the plant. That plant adapts to that drought stress. And certain things happen within that plant in a sequence. The first thing that happens, we get reduced shoot growth. So that's that growth above the surface. That gets reduced first. And cell elongation stops before cell division. And you're probably saying, well, why do I care about that? And let me show you why. Now, I'm not an artist, so don't make fun of my plant leaf. But this is a grass leaf. Kind of the way the grass leaves grow is we have a zone at the bottom of the leaf that's a zone of cell division. And so the cells are dividing and making more cells. And then these cells kind of blow up and elongate. And they do that again with water, like we showed with the balloon. And that pushes that leaf growth out. So what happens first is this zone of elongation slows down. So these cells are still actively dividing here, and they're kind of building up. So this has real implications on how that pasture is going to recover. So during a moderate drought, we can retain this leaf intact in that pasture. Water often will get almost what seems like compensatory growth in a thin animal. We'll get very fast recovery of that pasture because these cells are just hanging out here waiting for a little bit of water so that they can expand and push that growth out. And we'll almost get like compensatory growth in our pasture if we can just maintain this leaf during a moderate drought. The next thing that happens is we get increased root growth in the plant. And then we have accumulation of sugars and carbohydrates within that plant. Different plants in different parts of the world have different approaches to drought. In our humid area of the world, we have what we call dehydration postponement. And the first thing that happens is we get leaf rolling in the plant in many of our grass species. And corn is a grass. And anybody ever drive by a field of corn under drought stress? What's it look like? It's rolled up. And it does that to reduce the leaf area exposed to the sun and to reduce transpiration losses from that leaf, so water escaping from that leaf. And it happens in our pasture plants too. If you've ever seen a tall fescue plant under significant drought, the leaves are rolled up so tightly that it almost doesn't even look like a tall fescue plant anymore. Yeah. And again, it's trying to reduce that leaf area and reduce those transpiration losses.
Myself, usually.
The second thing that happens is it tries to maintain water uptake, and it does it by expanding the system. So it's shifting energy reserves to increase.
And if I find one that I can't find a calf in, I'll wait a week, get her back up, try it again. About 9 times out of 10, she's bred, and sometimes I still can't find a calf taking the sale.
This phenomenon that takes place, and corn breeders are trying to take advantage and breed corn that's more drought tolerant. And one of the mechanisms they do is try to select lines of corn that have increased root growth when it gets into drought stress. And the corn people have spent lots of money increasing drought tolerance of corn, and they have done it, significant increases, but only 9% under moderate drought, a 9% increase in yield. So it's certainly no silver bullet. The next thing that takes place, so we have leaf rolling, and then we have increased root growth. The next thing is what we call osmotic adjustment. And remember, I told you the way the cell stays rigid, or the plant stays rigid, is with turgor pressure. So there's our vacuole pushing out against the cell walls, keeping our plant upright and rigid. And then we get into a drought. We get the bread out. The way I take the question, our plant starts to wilt. Well, something called osmotic adjustment happens. And what happens is that the plant concentrates solutes inside of this vacuole. So the concentration of these solutes is higher on the inside than the outside of the vacuole. Everything in nature likes to be at an equilibrium. So what this does is increases the draw for water across that membrane of the vacuole, and it draws water in so that the concentration will be the same on the inside and the outside. And when that happens, we can reinflate that vacuole. Not a permanent fix. This is a temporary fix. That plant responding to that drought.
Grass through the summer.
If it gets bad enough and there's just not enough water, that vacuole is going to deflate, and that plant's probably going to senesce. Okay. So what happens
We have exactly figured it out.
Stomata are simply holes
And,
in the leaf. And these holes are found all over the leaf blade, and they serve several.
Had about was more than what we
Stomata are a little bit more than just holes. They have some specialized cells. And these are
but I would still rather have
these guards
rather have an open gate.
Those holes could actually open and close. Okay? And there's several roles of the stomata, and one of the important roles
At cow price.
escape from the leaf. So water moves through the leaf, roots of the plant, up through the stem, and then through the leaves and out the stomata. And it's kind of like a radiator, it's kind of cooling that plant down. So cooling of that plant leaf is one of the functions of the stomata. The other
I'm not. I can
it allows for gas exchange. So we need carbon dioxide for photosynthesis to take place within that leaf, and we need to let oxygen out. And those holes let that gas exchange take place. So when we have stomatal control taking place and those stomata close in that leaf, two things happen. We get a rapid increase in leaf temperature, and that's the beginning of the end for that leaf, and then we limit photosynthesis because we don't have gas exchange. And this happens, all these steps happen in a sequence. So we want photosynthesis to go on as long as we can to build sugars and carbohydrates so that they'll have energy to persist during that drought. So eventually that leaf dies. And the plant's doing that as a survival mechanism. It's sensing that it has so little water that it wants to concentrate that moisture at the growing point of the plant so that it can maintain that growing point and come back after that drought stress is over. What I want you to understand is that it's important to let these steps of adjustment to take place in our pastures. One of the worst things that we could do during a drought stress is come in and graze all the leaf area off our pastures. If we come around that rotation and we get back to that first paddock and the pastures haven't regrown, don't graze that leaf area off. Put them in a sacrifice area, maybe our weakest pasture on the farm, and feed some hay. And your neighbors are going to make fun of you because you still have grass in your pastures, but that's okay. Because after that drought stress is relieved, your pastures are going to jump right back. Their pastures are not going to recover quickly. So it's important to let this happen. The worst thing that we can do on a farm is what I see many producers do during a drought stress. They just open all the gates up and let those animals walk around that farm, and they just pick every piece of leaf blade off the entire pasture area. That's very, very stressful in those pastures. All right, we can't predict or prevent a drought from happening, but what we can do is manage for recovery. Again, we're managing for drought, not just during a drought, but every single day. And there's some things that I want to talk about that I think are important parts of drought management in pastures, and things that we don't commonly associate with drought, but soil fertility is one of those. And certain nutrients are involved in water relations to the plant and potassium.
It's hard. I mean,
Nutrients in our pastures. Things that I want to stress today is that when we lose stands of pasture to drought, in many cases, it's not just the drought that's causing that stand to die. It's a series of stresses on that pasture. Many times those stresses involve things like poor soil fertility, so that plant's under fertility stress, and then we've got poor grazing management, and then the drought comes along, and it's like the straw that breaks the camel's back. It causes that stand to die, but it's just not the drought. It's those other things that are on that plant. So part of a pasture management plan should be to relieve as many stresses on that pasture as we possibly can through good management prior to that drought stress. A well-managed pasture in most cases is going to make it through a drought. It's those ones that are really handled for the drought. Those are the ones we're going to lose. They have the small root systems and the poor fertility status. They have been under significant management stress. And then pH 6 to 6.4. what we're really doing is relieving stress from that pasture and bringing the pastures to grow after that rain comes. So
There was a shop building there, it's about 20,
recover much more quickly.
they were
A little bit about nitrogen fertilization. Of course, we want
Yeah.
nitrogen fertilizer applications during a drought stress. We also want to focus on
Really?
building strong nitrogen cycles in our pastures, especially at 70% nitrogen. We really got to
everything, I mean, that's
reducing and maintaining legumes within our grazing systems that are going to bring nitrogen into our grazing systems. We want to have organic nitrogen sources if they make sense economically, and then use controlled grazing. And you're saying, now, what's controlled grazing have to do with nitrogen cycles in pastures? Well, controlled grazing is allowing us to get more uniform distribution of dung and urine within those pastures and building these stronger nutrient cycles within our grazing systems. All right. A lot of times our drought occurs in the summer months, and I think we're ready to start. And if we protect our pastures during this drought stress, a little bit of nitrogen in late fall, we can really produce a tremendous amount of growth when that fall rain comes. And it's going to come. Sometimes it's later than we'd like, but it'll come. And if we're ready to grow grass, we can accumulate a lot of stockpile grass that's going to give us some deferred grazing during the winter months. And then the last thing I want to mention is something that the turf guys have been on to for years and years, and us slow forage guys haven't really picked up on it, but that's fall fertilization. And we're not going to get a lot of growth from a late application of nitrogen in the fall, but we will get those plants ready to grow. And that's important. We're going to increase tillage
Fall as well
and
for the cat
increase
pool.
the health of that pasture, and we're going to get off to a good start that following spring. And it doesn't have to be a lot of nitrogen.
Sure everything's good left over.
In late fall can really increase and help revive that pasture to farm. All right, grazing, I think, needs to be a central part of a drought management plan. We want to get healthy root systems in there, so we want to prevent overgrazing. We've got 3 plants here, one continuously stocked, one rotationally stocked, and then one that we don't use very much. And look at the difference in the size of the root systems. Just by how we manage these pastures, we can really increase the volume of that root system. One of the first things that people notice when they switch from a continuous to a rotational stocking system is that their pastures grow longer into a drought stress, and they come out of that drought stress much faster. And that has to do with what's under the ground that we're doing. It has to do with that root system. And the effect can be quite profound if you've ever witnessed that. We want to maintain a positive carbohydrate status in our plants, and we do this by resting our pastures, and having control of our grazing gives us that ability to rest those pastures. And then we want to maintain residual leaf area. Residual leaf area is important for photosynthesis, but it also does other things, especially in a drought. It shades the crown of the plant, so it's modifying that microclimate right near the surface of the soil. It reduces soil moisture loss when we have a little bit of residual leaf area on our pastures. And it allows for that compensatory growth if we get into a moderate drought, and we can maintain that leaf during the drought. So just to kind of sum things up,
I think
when we
No.
think about drought management, we want to make sure that we remove stresses from our
Didn't have
pastures.
enough
One of the
in the new-
stresses is low fertility. We want to allow pastures to acclimate to a drought. Remember,
rotating these
going from wet water status to a drought
plants and how to split it from there.
status is not like flipping a switch.
One thing I did was make it to where
Happen to that plant. And allowing those plants to acclimate to that drought can be pretty important. We want to rest pastures between grazing events and after drought stress is over. We want to leave plenty of leaf
and
that's going to
I remember when I was really bunches
that's going to
and they'd shoot for the shade before they was all done drinking and
drought stress.
back getting enough.
It's going to protect the crown of that plant during that drought stress. And if we get around our rotation and our pastures having regrown, we got to just bite the bullet, put those animals in a sacrifice paddock, and feed some hay. And that's probably one of the best decisions that you'll make in terms of your drought management plan, because you're protecting all of your other pastures on that farm.
You don't think about start bunching them up. They all need access to
We want to avoid multiple stresses on our pastures. If we are, pastures are going to be much more robust and are going to weather a drought much better.
I That I couldn't.
And it never hurts to ask the good Lord for it. And that's all I have, and I'd be happy to answer any questions. I'm sorry if you're disappointed and I didn't have a silver bullet for the drought problem, but I think the silver bullet is really managing it, and we should never forget that. All right. Probably a little bit, yeah, probably around the killing frost, I guess. I generally tell people in our area that, you know, in November around Thanksgiving, and our killing frost on average occurs about the 14th of November. Yeah. It's better if you can put it on a little bit early and get some have the moisture to do it. Any other questions? Yes. So the question's about feeding hay and damaging that sod. And I think you can do significant damage to a pasture sod when you feed hay, and you can just look and see that physical damage to that sod. I prefer, and you know, and you can debate this, but I prefer to take hay and I prefer to roll it out. And so we move and move the feeding locations around, so we try to limit the amount of damage we do on pastures. That has another benefit. When we move those feeding points around and roll that hay out, we get a better nutrient distribution from that hay. Hay has quite a bit of fertility value, and we're going to talk about that this afternoon in building and maintaining soil fertility. But we've got to look at hay as more than just a feed source for our livestock. It's also bringing nutrients into our grazing system. There can be significant quantities of nutrients into our grazing system. So getting that hay distributed will limit damage, physical damage from the animals, and also get those nutrients spread around. I always recommend feeding hay up to your worst paddock that you have, and then feed hay in that worst paddock. Where do people like to feed that? Yep, where it's easy. So if it's in a paddock that's right by the gate, you just drop the bale and run, right? So it takes a little bit more effort, but I think as an overall part of a fertility management plan, we should try to be moving our feeding points around. There was another question back there? Go ahead. Not necessarily. I think that the time period is going to change with the season. So in the spring, you want to start and have pretty short rest periods because the forages are really actively growing very quickly. And you want to start grazing a little bit before you think you should in the spring, and so you can create kind of a stair-step growth pattern in your pastures. And as you rotate through there very quickly, don't worry about grazing everything down, but rotate really quickly. As things start to dry out and temperatures increase and photosynthesis decreases in our cool season grasses, we'll want to slow that rotation down. So where you might have a 2-week rotation in the spring, you could have a month or even longer in the summertime when those pastures aren't actively growing as well. There's several different categories. We have our native warm season grasses, which would be adapted to West Virginia. We use a lot of Bermuda grass. We can use crabgrass in a grazing system. And I know that goes against a lot of people's grain, but crabgrass if it wasn't for crabgrass and wiregrass or common Bermuda grass in the south side of Virginia, we'd have a lot of hungry cows. And the other ones we can use are some summer annuals like sorghum Sudan or Sudan grasses, which are warm season grasses within grazing systems. Is there any other questions? Well, thank you for your attention and hanging around to hear this talk today. And I'll be here for the rest of the day if you have any more questions.